Hello, everyone, and thank you very much for attending my session today about Kubernetes at scale. My name is Xavier Avrier. I'm a solutions architect at Giant Swarm, where we do manage Kubernetes, and I focus mostly on on-premise and infra VMware kind of implementations. And today we're going to talk about cloud-native platforms and how to make an effective one with kind of a nerdy and fun way, fun analogy around the theme of superheroes. So as you know, superheroes, they solve pretty complex problems, I would say. When you watch the Marvel movies, there's explosions everywhere, there's a lot going on, they have a lot on their plates. So each superhero has a specific skill set, specific superpower, but just overall, they work much better as a team to solve bigger problems. And this is kind of like Kubernetes in a way. You have this platform and a lot of tools around the ecosystem. You can't just have Kubernetes by itself. It just doesn't scale. And this is kind of a way to visualize this, this thing. Like you have so many things that could go wrong by running a cloud-native platform, and just having two guys running that won't be enough. Like if you sent Chris Pratt, I can't remember his name in the movies, against Thanos, he would get crushed in like 5 seconds. So we're going to need a bit more than that. And on screen, I had a tweet between Craig McLaughlin and Joe Beda, which are two of the co-founders of Kubernetes back from their days at Heptio, which later on came to be acquired by VMware and became the Tanzu platform. And basically what they are saying here is that Kubernetes is just one piece of the puzzle. This is not like your end goal. In an ideal world, we wouldn't even think about Kubernetes. It is just here to provide resources, the infrastructure, so you can focus on the actual business applications that provide value to your organization. And in order to have this platform, you have to choose components. So you've probably seen this slide several times, like a lot of presentations use it to depict the complexity of the CNCF and open source ecosystem. There's many different projects that solve different problems in different ways. So there will always be like different ways to solve something. You just have to pick one. Just like there's like millions of Marvel superheroes, you won't find all of them in one movie. It just wouldn't really work. It would be too busy. So this is kind of our superheroes team today. Obviously, we would have much more than that, but we are going to focus on these sticks for now because we only have 25 minutes. So we have top left, we have Nick Fury, who's our kind of manager taking care of GitOps. Professor X, who can read into Kubernetes mine, obviously, taking care of observability. The Hulk will bring our infrastructure and our server racks and taking care of the infrastructure. Iron Man is like the high-tech, the cool guy doing Kubernetes. Spider-Man connects everything via spider webs. And Captain America will protect our environment from threats with the magic shield. So let's go ahead and start with Kubernetes. Just a quick slide, from the early days of containers, you have Robert Downey Jr. in his cave in the desert, building like this super armor with scrap metal. It works, it's quite rustic. Later on, around 2012, you get Docker that simplifies the management of containers and provisioning, storage, networking, etc. Finally, we got Docker Swarm, which delivered clustering across Docker nodes, And finally, around 2015, Kubernetes became the kind of de facto standard in the industry, being backed by Google as the main container orchestrator platform. And this is kind of the final form of our Iron Man armor. So this is how I feel when I am on an incident for a customer or debugging something in Kubernetes. There's all these different things going on all over the place, the ingresses or kubelet API, your fit your gates. So Kubernetes is a very complex platform. There's a lot going on, but it's very powerful at the same time. You get rolling updates. Everything is declarative, which is great for managing our environments. Self-healing, extensible for third-party projects, and portable across infras. Meaning your applications running in Kubernetes on vSphere can just as well run on Kubernetes in AWS, Azure, or wherever. And our first team member is going to be infrastructure lifecycle and Kubernetes lifecycle. So in order to do that, we will rely on Cluster API, which became the industry standard in the last few years as a way to provision infra to back our Kubernetes clusters. So in order to have a Kubernetes cluster, you need nodes. To have nodes, you need VMs or instances. And this has to be somehow done either by humans or by operators. So in Kubernetes, we have this project that will take care of bootstrapping the OS via Cloud Init or Ignition, according to the different US that you will use. KubeADM is the default Kubernetes bootstrapping provider. It will turn your KubeADM config into an Ignition or a Cloud Init script. And yeah, so Flatcar, Ubuntu supports various types of operating systems. And this is pretty much how it works under the hood. There's a set of four operators, so controller with a bunch of CRDs. We have the main KPI controllers, the core controllers, that take care of the life cycle of our clusters and our nodes. We have a bootstrap operator that is responsible for turning our KubeADM config into an Ignition or a Cloud Init script. So it can be like, how do you want to bootstrap the node? What files do you want to create in the OS? What SSH users? If you want to run commands before or after KubeADMs, all these things can be done. Can be helpful if you want to kind of add features that are not in the controller, like adding static routes or adding host records, this kind of stuff in kind of complex environments. Can be pretty handy. Our third controller is the control plane operator, which takes care of the Kubernetes API. There you can configure your API server, control manager, scheduler, and etcd. And finally, just like we have the core operator, we have an infra operator that will take care of reconciling our resources on the infra. So creating EC2 instances, VCD VMs, VApps, load balancer pool with backend servers, virtual services, basically all the skeleton that we need to run our Kubernetes cluster. And it's maybe a bit small, but down at the bottom we have the list of the supported providers by Cluster API. So there's quite a few, and the list is growing day by day. But in the case of VMware, we currently have VMware Cloud Director and vSphere. And this is an example of what it looks like when you take a look at the custom resource in Kubernetes that defines the template that you use to deploy a virtual machine. So you can have different node pools, which will be different sets of VMs that have different configurations. For instance, if you're running AI in some node pool and you run some other more traditional workloads, you don't want like 32 CPUs for your basic stuff. So you can have different node pools and have different configurations. So for instance, we set which data center to deploy to, data store, disk size, etc. It's just an example, just a few fields that you can set, but there's a lot more. Kubernetes Cluster API will look at that, and then it will interact with the VCD or vSphere API accordingly. Our next superhero is Spider-Man. So I used DALL-E 3 to generate the pictures, the visuals. Some stuff is a bit weird, like Spider-Man has a mouth. It's the AI weirdness that is going on. So basically, the idea is that Spider-Man connects things with his spider webs. Couldn't come up with a better analogy, so we'll have to work with that. And the first point of connectivity I wanted to touch base on is the container network interface, so the CNIs. The CNI is responsible for connecting your containers to the physical network and creating connectivity in between your various workloads. So I just wanted to touch base on this because CNIs are often overlooked when you take a look at clusters in Kubernetes environments. But actually, there are a lot of CNIs that solve different problems. You get your Calico, Flannel, Antria for VMware, or NCP. I don't know if it's still in use, but we also have Cilium, which is becoming more and more popular these days, backed by Isovalent. And Cilium offers, by default, native support for eBPF. So instead of having your routing done with NAT rules and IP tables, which is managed by kubeproxy, you would have all your routing and all your networking done directly in the kernel of your Linux OS. So by having that, you get rid of middlemen, so less overhead, and also you get observability capabilities. So you can watch like eBPF events, and you can see kind of what's going on, create network policies, and just overall improve performances. And they actually have a tool called Hubble, like the telescope, which looks like that, and it allows you to visualize your network flows. So at the top right, you can see that I have a filter for dropped packets. This is great because sometimes if you have like a secure environment, you will want to whitelist traffic. You don't want all traffic to be able to happen and have random pods talk to the Kubernetes API. You will want to tighten all that down, at least the kubesystem namespace. And then you can create your network policies or your Cilium network policies to allow traffic into what you want to whitelist. So in this case, we have dropped traffic to port 3128, which is our proxy, HTTP proxy. It's just because we forgot the CNP, the Cilium network policy in this case. And then we found that, we created the CNP, and traffic was forwarded after that. And the CNP looks like that. This, you get your source, your destination, your port, etc. And yeah, some basic Kubernetes stuff as well in terms of connectivity. We have our stickman on the right, on the left that wants to access specific deployments, applications on the right. So we have a couple of deployments and a service. So if we want to expose them, we are going to need ingress controllers, so your Nginx, traffic, API gateways, etc. Ingress routers are going to be able to route traffic based on the URL that you requested and send you to the right deployments accordingly. These controllers need to be exposed to the world somehow. So we are going to need an IP address in the physical world. For that, we're going to need a service of type load balancer. And this can be reconciled in our infrastructure by what is called a cloud provider interface, so a CPI. So if you take a look at AWS, Azure, and VCD, let's say, they all have like a CPI. So when the CPI sees that there is a new service of type load balancer, for instance, in VCD, it's going to create a load balancer pool, add the control plane VMs, IPs into the pool, create a virtual service with an IP, attach these two, and once you reach this virtual IP, you get routed to your ingress controller, which will route your request based on your URL. But an IP is cool, but it's not great, so we're going to use the DNS records. So external DNS is the main project that watches ingress resources to create your DNS records in public or private DNS providers. Cert Manager will take care of our certificates, and we can also add some sort of authentication and SSO into our environments. So on screen I have DEX. DEX is one of the main SSO authentication OIDC providers, but in Kubernetes 130 or 131, I'm not sure, there is a new feature that is being implemented in the Kubernetes API, so this might become like integrated into Kubernetes, so this might become might become obsolete in the next few months or /years. Our next guy is Professor X with telekinesis and being able to read into people's minds and also into Kubernetes and eBPF mind. So I want to start with the 3 pillars of observability. So these 3 pillars are applicable to Kubernetes, but also to any type of monitoring of observability in the world. You have the first one, which is monitoring. It refers to your metrics. It will tell you when something goes wrong. The second pillar is logging, so you know what logs are, like events and output of your various containers and workloads. This will tell you what happened, what caused the issue. And finally, tracing will help you identify where the issue occurred. So for instance, in like a more traditional like legacy application, monolithic, where you have everything on one VM, one server, it's fairly straightforward to figure out where things go wrong, but in a distributed system like Kubernetes, you're going to have microservices in maybe different namespaces connecting to each other with services, ingresses. So it's kind of scattered everywhere. So you need to figure out a way to trace that request on its path from source to destination. And by using tracing, we are going to be able to identify where latency happens, where we get timeouts, and these kind of things. And the main projects around observability are actually being driven by the Grafana group. So we have Grafana for visualization, but they are also behind Loki, which is a log aggregation system. They are behind Mimir, which is a fairly new time series database. So you might be you might be familiar with Prometheus, which is also a time series database, but this day we are seeing more and more of Mimir. We are migrating to Mimir because we figured out it's more efficient. Mimir will collect our metrics from various agents. So for instance, you have a Prometheus agent that will scrape metrics from your metrics server, kubestate metrics, and any other exporter that you might want to use for your apps or for whatever else that you want to expose. And on the other hand, Loki will take care of getting some logs pushed to it via agents as well. So basically, we would get like the usual ones, which are Kubernetes events, container logs, Kubernetes audit logs, if they are enabled, and the machine audit logs. So the actual nodes, the OS that is running our Kubernetes clusters. And based on all that, we can visualize the data in Grafana and get alerted based on rules by Alert Manager. We can get paged at night, etc. So based on all these metrics. Then we have Captain America taking care of the security of our environment. These are the three things that everybody should be doing regardless. So we have role-based access control, who can do what in the K8s API. PSA, so pod security admission, what our pod configuration should be like. And network policy, what can talk to what. So these three things are core to Kubernetes, and everybody should be doing it at least. Just to show it, this is what our back looks like. So on the left, we have a cluster rule, basically telling us that we are able to list the namespaces. This is just an example. And on the right, we apply this cluster role to our OIDC group. So if your user authenticated using OIDC and is part of these two groups, list namespace, kubeadmin, it will be able to list all namespaces in our cluster. We have a Kyverno cluster policy. So you have various policy admission controllers. There's Kyverno, there's OPA, there's a bunch, or might be the two main ones. But this is what Kyverno looks like. So basically here we are saying that any pod should have at least run as non-root set to true. If it's not set on the pod, it won't be admitted in the Kubernetes API and it will be rejected. This is a way to ensure that our environment is secure to at the very least. And network policies will allow us to say what can talk to what. So in this case, we have a source, destination, and a label. So in here, we allow the metrics server to talk to the Kubernetes API in the case of our observability stack. And then we have other projects if we want to go a bit further and improve our security posture. On the left, we have a CNCF graduated project backed by SysDig called Falco, which provides runtime threat analysis, threat detection. So it will watch the syscalls in the kernel of the nodes. So basically, you can identify if something is trying to write to a path it shouldn't be writing to. Suspicious binaries, it will watch eBPF events, hence the need for the benefit of running Cilium, because we get observability into our network stack. And on the right, we can get some reporting. So we have vulnerability scanning against, for instance, CVEs, secret leaks. If you want, you don't want to push secrets into your unencrypted secrets to your Git repo or something like that. Compliance report, if you use VROps or the likes, you want to be able to scan your environment and make sure you are compliant with NSA, CISA, and some other bench like frameworks that might be relevant to your organization. And software bills of materials might be interesting for auditors and other purposes. And this is what a vulnerability report looks like. So you would get the same resource in Kubernetes, but if you export it, you visualize in Grafana. You can see your CVEs. So we have 1, 2, 4 CVEs according to its critical levels. And basically, you get visibility into your security posture for your clusters. And finally, we have Nick Fury, the manager of our Kubernetes platform and our cloud-native environments. So he's kind of this guy, like, you know, in this big ship running in the air. And he's got everything stored in boxes, containers. But basically, I'm trying to show that everything is stored in a Git repository. So there is a working group at CNCF called the GitOps working group. And this working group came up with 4 basic principles that every GitOps environment should abide by. The first one is that it is declarative, which is a core concept of Kubernetes. So all your system must be declarative, and I mean all the system. You don't want to have half of your resources defined in GitOps and the other half imperatively created by colleagues, customers, etc. Otherwise, if say something happens and you want to recreate your cluster, you're only going to have half of your environment. So either you're in or you're out. GitOps should be all in. It has to be versioned and immutable, which is a core concept of the Git protocol. Ideally, you guys shouldn't be going into main and rewriting the history of your repo. That's not right, so you shouldn't be doing this. This is what we hint at with the fact that it is immutable and version if you have to roll back, if you figure out something is wrong with your environment. Pool-based mechanism compared to like an Ansible runbook where you would have to go and actively run the playbook and push the changes to your environment. In the case of GitOps, we have an operator that runs in our Kubernetes clusters, watches the resources in the source, and pulls them back and applies them to the Kubernetes API. And finally, another core concept of Kubernetes, it has to be continuously reconciled, meaning we have reconciliation loops. It's not like, again, pushing a change. We always check for changes all the time. So you make a change in your Git repo, you wait 2 or 3 minutes, and then, boom, it's done. It's in your Kubernetes API. This is the 4 principles we should abide by. And this is what it looks like for FluxCD. So I chose FluxCD because this is actually the officially recommended project by the CNCF. If you go on this website, I mentioned this one, the GitOps repo. It's from I can't remember the URL, but it's on a website, and they recommend FluxCD as the proper CNCF GitOps solution. So what we have here, there's different ways to do this. I showed the Helm controller, which is basically a good way to manage the life cycle of your applications. So you could have the customized controller, which will just apply YAML manifests into your Kubernetes environment. But in this case, we have a source controller that will watch our Git repo. It could be like a cache registry, a Harbor registry, or whatever. It has to be OCI. And could be a Helm repository as well. But then we have a source controller. When it sees that there is a new commit in our repo, it will pull the artifacts locally onto the controller. The Helm controller will pick up that there are new values for our Helm charts. There is a new version of our Helm charts. Something changed, and it will apply new Helm revision to our application. That way, when you do like Helm history, the name of my chart, you can see all the revisions of your charts, and you can go back, see the values, the manifests, etc. And again, obviously, it comes with its own set of CRDs. But this is pretty much like what most companies do in terms of application lifecycle when it comes to using FluxCD in production. So that's it. I just wanted to show these six components, these 6 superheroes. I'm just going to wrap it up. Thank you very much for listening. We are over there at booth 530. I don't know if you have any questions. In the meantime, you can scan this thing about the Broadcom rewards program. I'm not sure what it does, but it's there if you need it. Yeah, I will be happy to answer any question if you have any. We have about a minute and a half. Yeah.